Okay, we're going to be covering integration by substitution. Now remember that integration is the opposite of differentiation. So for every differentiation rule, you have a corresponding integration rule. And the rule for integration, which corresponds to the chain rule for differentiation, is called integration by substitution. So it's best to just start with an example. Suppose we want to integrate, say, 2x plus 3 to the power 5 dx. Now you might think, well, this is easy. This is the integral of something to the power 5, and I know how to do that. It's just that something to the power 6 over 6 plus c, right? So, but let's check. If I differentiate this, what do I get? Well, the sixth comes out. Then I have to differentiate 2x plus 3 to the power 6. That gives me, that's differentiating something to the power 6. I have to use the chain rule. Is 6 times that something to the power 5 times the derivative of the inside. Okay? Which is 2. So the 6th is going to cancel with the 6. But we've got a problem here because we've still got a 2 left over. So that means when I differentiate this, I don't get 2x plus 3 to the power 5. Rather, I get 2 times 2x plus 3 to the power 5. So we're going to have to take into account the fact that there's a 2x, there's a 2 multiplying the x inside the bracket there. You somehow have to undo the chain rule. So the way you do it instead is as follows. You try and rewrite your original integrand in terms of a new variable u. So you let u equal to the inner function. This is a composite function, right? It's the inner function is 2x plus 3, and the outer function is to the power 5. So first of all, you calculate 2x plus 3, and then you put it into the machine, which raises everything to the power 5. And you let u equal to the inner function, which is 2x plus 3. Okay? So then you notice that if you take the derivative, you get 2. That's easy. And now I'm going to do a very strange thing. Up to now, we've regarded du by dx as an indivisible quantity. In other words, it's not du over dx. We've sort of laughed at anyone who imagined that this was du over dx. But now I want you to imagine precisely that. So I'm going to liberate the du from the dx and let them stand apart on their own right. So I'm going to multiply through by dx on both sides here. So I get du is equal to 2 dx. It seems rather strange, but it's absolutely okay in this situation. But if I want to solve for dx, I can say that du over 2 is equal to dx. And that's great because that allows me to rewrite each and every part of the original integral in terms of u. Because this part of the integral is 2x plus 3 to the power 5, I can write that just as u to the power 5. There's also this part of the integral, the dx, which I can now express as du over 2. Okay, so my original integral can be written as the integral of u to the power 5 times du over 2. Now this is a much easier integral. First of all, this over 2 is just a constant, so it comes out the integral. Integrating a power is easy. It's u to the power 6 over 6 plus c. And in the last step, I should just replace u with 2x plus 3 because the original integral was expressed in terms of x, So I must express my answer in terms of x. I can't express my answer in terms of u because that wouldn't be answering the original question. So in the last step, which you shouldn't forget to do, I should replace u with 2x plus 3. Okay, and that is the final answer. And you can check that that's the final answer. Let's see. If I differentiate this, then what is it? It's exactly what I had before, but now I've magically got this factor of a half in front. If you trace back where that factor of a half came from the du over 2, which came from du over 2 being equal to dx, which came from du equals 2 dx, which came from the derivative of u with respect to x. So it's precisely this step here which produced the magic factor of a half. You see, now when I differentiate, I'm going to have a half in front, so that's going to cancel the 2, and now the answer is correct. Okay, this is the method of integration by substitution. Okay, our first example. Calculate the integral x cubed times cos of x to the power 4 plus 2 dx. Right, so we recognize that a component of this formula is actually a composite function, namely this component here, because this is really two functions composed together. First of all, you calculate x to the 4 plus 2, and then you take the cos of that. So usually when you're attempting the integration by substitution technique, you let u equal the inner function you identify a composite function and you let u equal to the inner function inside the composite function. So in this case, it's the x to the 4 plus 2. Now note what happens when I take du by dx, which I have to do because I have to calculate du. Du by dx is 4x cubed. Therefore, I can multiply both sides by dx. I get du is equal to 4x cubed dx. Now stare at the integrand carefully. We've got an x cubed and we've got a dx. Together they make x cubed dx. I like that. Just like mank and and makes mankind. Anyway, we've got an x cubed dx, but du is 4x cubed dx. So I can just say, oh well, du over 4 is x cubed dx. And that would completely account for this part of the integrand. The x cubed dx can be replaced with du over 4. And this part over here can be replaced with cos of u, because u is x to the 4 plus 2. So now we can rewrite the entire integral, which is the integrand and the dx part, in terms of u. It would just be cos u, that would be this part here, and then I've got a du over 4, which caters for the x cubed dx. This is an easy integral to do. The factor of a quarter can come out in front of the integral, that's no problem. And then I'm integrating cos of u. Integral of cos is sine. So I get a quarter sine u plus c. And you can put the plus c in the brackets like this, or you can leave it out the brackets, because a quarter times a constant is still a constant. Okay, so sometimes you might prefer just to write it like this. That's okay as well. Don't forget the last step, which is to replace u with x to the 4 plus 2. Good. That's the final solution. Now we should check the solution. We should check whether the derivative of this function is equal to x cubed times cos x to the 4 plus 2. Because that's what we're saying here. We're saying that this is the antiderivative of this. In other words, the derivative of this is equal to this. Let's check. So I calculate the derivative of a quarter sine x to the 4 plus 2. What do I get? Well, the quarter comes out in front. Then I'm differentiating the sine. The derivative of sine of something is cos of something times the derivative of that something by the chain rule, which is 4x cubed, because the inner function was x to the 4 plus 2. And now I magically see that this 4, which comes from the chain rule, is going to cancel with that 4, and I'm left with cos of x to the 4 plus 2 times x cubed, which is exactly what I had. Okay, so it's correct. Okay, our second example is the integral of the square root of 5x plus 2 dx. So if you're going to attempt the method of integration by substitution, you should recognize that some part of your formula that has to be integrated is a composite function, which is the case here, because first of all you calculate 5x plus 2, and then you take the square root of that. And usually what you can do 9 times out of 10 is you simply let u equal to the inner function in that composite, which is 5x plus 2. Right? So therefore du by dx is equal to 5. So therefore du is equal to 5 dx. By the way, instead of doing this in 2 steps, first of all calculating du by dx, and then multiplying through by dx to calculate du, from now on, we're just going to directly write down du is equal to 5 dx. We're not going to do it in 2 steps. Okay? But now we've got du is 5 dx, which is great, but we've just got a dx there, so we can write the dx as du over 5. Now we can cater for all parts of the integral, because the dx is catered for as du over 5, and the square root of 5x plus 2 is catered for as being just the root of u. So we can rewrite the integral together with the dx completely in terms of u as the integral of root u du over 5, which is an easy integral to do. The factor of a fifth can come out the integral, and I'm left with integrating square root of u. You can always write square root of u in a perhaps easier to understand form as u to the power of a half du. When it's written in this form, it's much clearer how to integrate it. The integral of something to the power n is x to the power n plus 1 over n plus 1. So I get u to the power of a half plus 1 is u to the 3 over 2 over 3 over 2. And I'll just leave it like this. There's no need to simplify by multiplying through. You can if you want, but you can just leave it like this. And then I've still got the plus c. Good. The last step is always to rewrite u in terms of x. So I get a fifth times u is equal to 5x plus 2. Okay. We should always check whether our answer is correct. So let's do that. I'm going to differentiate this and see whether I get the square root of 5x plus 2. So let's do that. I differentiate a fifth times 5x plus 2 to the power 3 over 2 over 3 over 2. What do I get? Well, these are just constants, so they can come out in front. And I'm not going to simplify them. I'm going to leave them as separate factors because they each have their own individual role to play. Now I've got to differentiate 5x plus 2 to the power of 3 over 2. The derivative of something to the power n is n times that something to the power of n minus 1 times the derivative of the inside. So I get 3 over 2 times this thing to the power of a half times the derivative of the inside, which is 5. Okay, and now you see how all the factors are going to cancel. This 5 is going to cancel that 5, and this 3 over 2 is going to cancel that 3 over 2, and I'm left with the square root of 5x plus 2, which is right. Okay, our final example is the integral of square root of 1 plus x squared times x to the power of 5 dx. Good. So again, we observe that here is a composite function. So usually if we're going to try and do an integration by substitution, we'll let u equal to the inner function. So we could let u equal to 1 plus x squared. Then what would du be? So let's try that. Du would then be 2x dx. Right? It's du by dx, which is 2x, times dx. And that's okay. We don't recognize automatically a 2x dx here, but I can do a sneaky thing. In this x to the power 5, I can separate it into an x to the power 4 times an x. And right? So I can write that x to the power 5 as x to the power 4 times x. And now I recognize x dx can be written as du over 2. Okay, this is how you do integration by substitution. You look at various components of your formula, your original formula, and you try and write them either in terms of u or du. And sneakily we had an x to the power 5. We recognized that if we could separate off a factor of x from that x to the power 5, then I could account for that factor of x as being part of the du term. Now I'm still left with this, but that's okay, because this part of the formula can be written as square root of u, and I've got an x to the power 4 left over. That's no problem, because x to the power 4 can be written as x squared squared, right? And x squared is u minus 1. Okay, so I can write that x to the power 4 as u minus 1 squared. And in this way I've cleverly been able to write every part of my original integral in terms of u. So what are we left with? We're left with calculating the integral of root u times u minus 1 squared du over 2. Okay, this still needs a little bit of work, but we can do it. Let's take out the factor of a half and multiply through here. This is u squared plus 1 minus 2u. Multiply that with the factor of square root u, which is u to the power of a half. I get u squared times u to the power of a half is u to the power of 3 over 2. And then I've got a minus 2u times a u to the power of a half is minus 2u to the power of, this was u to the power of 5 over 2. Now I've got a 3 over 2. And then I've got a plus 1 times root u is a u to the power of a half du. This integral can be done quite easily. I can write it as sum of 3 different integrals. Each of them is just an ordinary power law integral. So integral of u to the power of 5 over 2 is u to the power 7 over 2 over 7 over 2. minus 2 times integral of u to the power 3 over 2 is u to the power 5 over 2 over 5 over 2, so that when you differentiate it, the 5 over 2 is going to come down and it's going to cancel with the 5 over 2 below, and you'll get out u to the 3 over 2. Okay? Plus integral of u to the half is u to the 3 over 2 over 3 over 2. And I can put the plus c inside or outside the brackets, it doesn't matter. Right, I'm not yet finished. I should now replace the u's with 1 plus x squared. So the final answer is a half, and I've got a big bracket here. U to the power 7 over 2 is 1 plus x squared to the power 7 over 2. That's this term. And then I've got a u to the power 5 over 2. And then I've got a u to the power 3 over 2. Sorry. U is 1 plus x squared. Okay, that's my final answer.